In this video, we're going to talk about queues and decks. So a queue is a good example is a checkout line. And what are the behaviors? Can you randomly access it? Not if you don't want to get punched. Can you determine how many people are in the line? Yes. When is the queue full and when is it empty? So queues are a first in, first out, called FIFO, data structure. The operations are add an item, put it at the end, and remove an item, take it from the front. Or look at the first item, which is called peek. Now, we're going to go over some STL stuff for this, but you're also going to end up implementing this yourself. So the operations on a queue include add item, where we have enqueue, which is called enqueuing, and we add item I to the end of the queue, and then dequeue, where we grab the first member and return it. If we want to just look at the first item without removing it, we do a peek, and we'll need a function to init. STL implements a queue container, but not quite as expected because it has the following functions. We have push, pop, front, and back. In order to use the queue, you need to include queue, and it's defined as a type name with a default of deck, because deck is a bidirectional, we'll talk about in a bit. The core also includes size and empty. Note that in this case, pop removes the element but doesn't return it. Front and back return the element but don't remove it. Both pop and front and back have undefined behavior in the case of an empty queue, so you need to test around it. So here's a very straightforward example. We define a queue with a string. We push these are more than onto it, and we're going to read the first element, pop it, read the second element, and pop it, which would give us this and R. And then we're going to push on two more words, 4 words, and we're going to pop one and skip it. Then we'll read and print 2 elements, queue front, pop it, queue front again, and pop it. And then we're going to print the number of elements. Oops. And what it will print out is there are 4 words, because these are, and then we will push 4 words, and then we do a pop, and then print it out, and boom, we're done. So there's also the concept of a priority queue. It's similar interface as a queue, but the elements are read according to the priority. Push adds an element to the queue, and pop removes the next element, but not necessarily the first element added to the queue. Top returns the next element. Elements are sorted by default using the operator less than. The next element is always the highest element, i.e. highest priority. If more than one highest element exists, which element returned is undefined. So here we have a priority queue which we establish. We push 666, 222, and 444. We're going to read the top, and it is 666. We're going to pop it, and now we're going to read the top again, and it's 444 because it has higher priority by a value, and pop it again, and then we're going to insert 3 more elements and pop them appropriately. Now, skip one and then pop appropriately. Now, implementation of priority queue is much more complicated, and we won't cover how in this class. A deck is very similar to a vector, and it manages elements with a dynamic array, provides random access, and roughly the same interface as a vector. The difference is that the dynamic array is open at both ends. Okay. Whereas a deck is not. The deck is fast because you can add and delete from both ends. In order to use it, you must, as this should say deck, include deck, and allocators represent a special meta model and an abstraction used to translate the need to use memory into raw memory calls. Allocators provide an interface to create, destroy, and deallocate objects, and it's beyond the scope of this class, but you should just where they exist. Some differences between decks and vectors. Inserting row 2 elements is fast at both ends. Element access and iterator movement is a bit slower because you can't do random access. Iterators must be smart pointers of a special type rather than ordinary pointers because they must jump between different blocks. And decks offer no support to control the capacity and the moment of reallocation. Inserting and deleting elements in the middle is relatively slow, just like with vectors. And the iterators are random access iterators. We need to insert Dequeue. Why would we use it? We want to insert and remove at both ends. We don't need to refer to the elements individually. And it's important that the container frees memory when it's no longer in use. However, the standard doesn't guarantee this will happen. Here's a full-blown deck example where we can print all the elements. Here we push them onto the back and then push this on the front. And we can move an element from the front and the back, and we can insert another element into every element but the first. And change the size to 4 elements to resize it. And then print it again, separated by new lines. We will discuss implementation of these in the homework assignments. You can use STL, but for homework assignments, you're going to implement these yourself.